Still be able to pick up on his enthusiasm, only be remote. So we're going to hand over to John now, who by the power of technology should be able to present for the next 20 minutes. So handing over to you, John.
So, hello everybody. I hope you can all hear me. So, as Mike said, I apologize for not being with you in person today, so unfortunately I can't jump around in front of you. But instead, to make up for that, I do have control over the screen that you see before your eyes. So, for example, I can flash up a photograph of myself, and you'll see what I look like. In fact, I can do all sorts of smart things with this screen, so you're at my mercy for the next 20 minutes or so. Anyway, let's have a look at presentation for today, UVM Now or Never. So what I'm going to do is to give you our take on UVM as training providers. So I've worked for Doulos now for 22 years, and we've watched the rise of VHDL, Verilog, System C, and now SystemVerilog and UVM. And I'm really going to give you our view on the state of the market today and the state of SystemVerilog and UVM adoption. So I'll start off by talking about some basic facts about UVM. What's UVM all about? Well, UVM really allows you to capture best practice. And the best practice in terms of functional verification. And the key advantage for that is increased verification quality and the opportunity for all kinds of reuse. So that includes reuse of verification IP, reuse of test benches, reuse of tests, and also, of course, reuse of knowledge and skills and people. But the rise in the use of UVM is very much tied in with the success of SystemVerilog. So in parallel with talking about UVM, let's talk about SystemVerilog a little bit as well. So SystemVerilog has risen over the last few years to become the language of choice for really most companies in the world right now adopting advanced functional verification techniques. And the real reason why SystemVerilog has come to be so popular is that it doesn't tie you into any specific simulator vendor. So time and time again, we see companies making a commercial decision to adopt SystemVerilog because it's a language standard. So SystemVerilog really does represent a triumph of standardization. On the other hand, SystemVerilog is still a very large, complex language, and even today there are significant differences between different SystemVerilog implementations. In fact, in one of the previous verification features event, I think the one that was held in the UK, one speaker stood up and said one of the problems that they have right now with verification is that there aren't one SystemVerilog language, but 3 different SystemVerilog languages. And of course, they were alluding to slightly different implementations between different tools. So the history and the growth in use of SystemVerilog is very much tied in with UVM and with other standard verification methodologies. Because what's happened over the years is that the advent, the development of class-based verification libraries layered on top of SystemVerilog has really driven the unification and the development of a consistent implementation of SystemVerilog, and none more so than UVM, the universal verification methodology. So today UVM is actively supported by all the major and minor tool vendors, by which I mean they not only implement UVM in their simulators, but actively promote it and encourage their customers to use it. And so what we've seen is with each new, rather with the introduction of each attempt at standardizing a verification methodology, we've seen increasing convergence in SystemVerilog implementations. With each class library, each vendor has attempted to implement and support the class libraries of their competitors so as to pinch their customers, and that's really seen a rapid convergence in SystemVerilog implementations. Also, having 3 standards is much better than having 1 standard. And having 1 standard is much better than having 3 standards. So the arrival of UVM, a single universal verification methodology, has seen greatly increased confidence in adopting SystemVerilog. So what we're seeing is that with each new methodology culminating in UVM, the universal verification methodology, there's been a jump in SystemVerilog adoption. So let's have a look now at some of the basic facts around UVM. So UVM is an open source SystemVerilog base class library. It consists of SystemVerilog code. Of course, UVM exists to allow us to do constrained random functional verification, and in particular to build extremely configurable, flexible test benches. Because above anything else, UVM is all about reuse, as I said earlier, reuse of verification IP, reuse of tests, reuse of skills. And although the current UVM base class library is actually implemented in SystemVerilog, UVM has always had a mixed language vision. UVM has always been intended for use within mixed language environments, and I'll say a little more about that later in my presentation. So although UVM is a standard and it's an open source base class library, it doesn't give us everything that we need. In fact, in some ways, UVM gives us too much choice. And I say that because UVM actually supports a number of different legacy class libraries and supports backward compatibility with its parent class libraries. And that means that there's a lot of code kicking around in the base class library to support legacy environments. And because of that, users have choices to make when they start adopting UVM. So UVM helps by constraining the way that we use SystemVerilog, but we also need to constrain the way in which we use UVM to choose which parts of UVM we use and how we're going to use them. And that's why I say we still need a methodology even to use UVM. Just say a few words to explain the big picture of UVM, what it is, what it looks like. So UVM is used to build functional verification environments for doing simulation and for writing tests. So at the bottom of the slide here we have the design under test, the DUT. We then use UVM in order to write SystemVerilog code for building a class-based verification environment, a verification environment for exercising the design under test, written using SystemVerilog classes. And that environment has a consistent spatial structure. One of the main reusable building blocks here is the UVM agent. And an agent has an expected structure consisting of a sequencer and a driver, which drive transaction streams for exercising the design under test. The sequencer and the driver will drive transactions into the design under test. Then on the upstream path we have a monitor, and the monitor will look at all the pin wiggles on the design under test and then distribute those transactions to the remainder of the verification environment. When you come to use verification IP, for example, if you're using a standard protocol such as AXI, you might go and acquire some external verification IP and bring it into your particular verification environment. And at that point, you'll probably find that the verification IP that you acquire won't do exactly what you want it to do. And one of the big strengths of UVM is allowing you to customize and reconfigure existing verification IP. And UVM in particular provides 2 mechanisms for doing that, the factory mechanism and the configuration mechanism. I don't have any time to go into more details right now. I'll give you some links at the end of this presentation of where you can go and find further details if you're interested in drilling down into the fine details here. But suffice to say that one of the strengths of UVM is that it allows you to take existing verification components and then customize them and reconfigure them to the particular verification environment that you're building. So we continue to build up a verification environment using a standardized structure. And that verification environment then provides a body of code that we reuse as we verify our design under test by writing a series of individual tests. So tests are layered on top of our UVM verification environment. Large companies very often choose to have separate teams of test writers creating the tests. So big companies might organize themselves by having a group of verification experts who know UVM really well, who construct the verification environment, and then maybe separate test writers who build UVM tests layered on top of that verification environment. And those UVM tests would use these same mechanisms of the factory mechanism and the configuration mechanism in order to customize the behavior and structure of the verification environment. So let's have a quick look at some of the highlights of UVM, some of the buzzwords and things you should be looking out for as you start to learn and use UVM. UVM supports the separation of tests from test benches, as I've seen, so tests and test benches are kept separate. Communication within the UVM verification environment uses transaction-level communication, sometimes called TLM, or transaction-level modeling. Transaction-level modeling was imported from the System C world. UVM then generates test stimulus by using sequences. Sequences are an important part of UVM. As I've already mentioned, the factory and the configuration mechanism is used to customize and reconfigure existing code. Then there's a standard message reporting mechanism, a standardized way of ending tests, and the register layer, which is a very important element in UVM, used to abstract a register model. Okay, now let's move on and say a few words about interoperability and migration in UVM. So a lot of companies adopting UVM already have an existing legacy verification environment, perhaps written using OVM or VMM. So UVM actually had a long chain of ancestors, quite a distinguished family tree. The immediate parent of UVM was actually OVM. So the first version of UVM was literally OVM version 2.1.1 plus a Perl script, and that Perl script replaced all of the character strings OVM with UVM. So if you originally had an OVM description and you wished to port it to UVM, you would download the UVM class library, download the Perl script, run that Perl script on your OVM code, and convert OVM to UVM by changing the characters OVM to UVM. Well, that's how things started. UVM also inherited a number of good features from VMM on the Synopsys side as well, as it was brought into the Accelera Systems Initiative for standardization. So where we are today is that UVM represents the culmination of a string of standard verification methodologies. And right now, UVM is actively developed and promoted by all of the main EDA vendors. People often ask about OVM and VMM and whether they need to move from OVM and VMM and what's wrong with UVM, what's wrong with using OVM and VMM anyway? Well, OVM and VMM still work just fine. They're still supported. If you've got OVM and VMM code, well, those were great methodologies. They work just fine. Your code will continue to work. But frankly, it's not where the action is right now. So all of the momentum within the industry and the ecosystem has now moved on to focus firmly on UVM. And even the EDA vendors themselves who authored and brought into being these parent methodologies, OVM and VMM, are right now encouraging their users to move to UVM because it has become an industry standard. So now UVM is beginning to diverge from its parent methodologies. UVM has added new features to OVM, and some of the features of OVM are now being deprecated. So at Doulos, we continue to deliver OVM code as well as UVM code, but what we're seeing right now is that OVM code is starting to look out of date because the coding style that's now evolving in UVM is actually diverging from the coding style in OVM. And UVM itself is continuing to move on. So one of the reasons for UVM's success is that it's proved to be a very, very stable standard. The code base hasn't shifted much over the last couple of years since it was introduced. However, certain features are in progress, in particular the runtime phases. So moving forward, you can expect to see some changes in the runtime phasing mechanism of UVM going forward, and you can also expect to see further work in the mixed language arena. Meantime, if you want to migrate from OVM or VMM to UVM, or you want to continue to interoperate between OVM, VMM and UVM, then this is an extremely well-trodden path. So on this slide you can see a number of the resources that are available. You can go find white papers and training classes to help you make that migration. And in fact, at the DVCon conference this year, a number of users stood up and said how they successfully used these methodologies. Let's say some remarks about mixed language. So as I said at the outset, UVM was always intended to work in a mixed language world, although right now the implementation of UVM is in SystemVerilog. So when we start thinking about mixed language, we have to distinguish very carefully the level of abstraction that we're talking about. So to cut to the chase, at the register transfer level, mixed language communication is pretty much a solved problem. All of the vendors have got mature solutions here. Similarly, at the functional level, if we want to make function calls across languages, then it's pretty much a solved problem, and in particular the SystemVerilog DPI allows us to make function calls between SystemVerilog and C. But the interesting use case is transaction-level communication between languages. And that's where we're in a rather more interesting situation, because there isn't one solution out there, there's 3 solutions out there. In fact, it turns out that Cadence, Synopsys and Mentor each have working solutions to pass in transactions between a UVM verification environment and a System C transaction level model. Each of these solutions works fine. I've personally used them all and I can assure you that they all work fine. Unfortunately, they're all different to each other and not mutually compatible. So if you care about this, then maybe you should go put pressure on your vendors and start participating in the Accelera Standardization Organization to actually push toward a single unified standard for transaction level communication. So I've just got a few minutes left before I wrap up my presentation. Let me make some final remarks. And in many ways, this slide is the most important of my presentation, because there's kind of an open secret within the verification community that there's good news and bad news when it comes to the adoption of SystemVerilog and UVM. The good news is if you're looking to follow a standard path and a well-trodden path when it comes to adopting better and standardized and more productive verification methodologies, then SystemVerilog and UVM is definitely the way to go. The bad news is it can be expensive and there can be a lot of investment, and in particular there's a very significant learning curve involved in learning to use SystemVerilog and UVM. So a lot of managers that we talk to and a lot of newbies to SystemVerilog and UVM basically have the wrong expectations. Very often we pick up the phone to customers and they say that they are expecting, a manager in a team expects his team to learn and use SystemVerilog and UVM within 3 days of training or 5 days of training, say. And that's simply not practical. In the old days of teaching people to use VHDLs, we could, in the context of a 5-day training class, take an intelligent engineer and teach them to be project ready with RTL design, synthesis and test benches. When it comes to SystemVerilog and UVM, that's simply not true anymore. There is a significant upskilling necessary. So if you count out the number of days training that it requires, and this is just in the context of formal training, to take somebody to nothing to project readiness with SystemVerilog and UVM, well, in the case of the DUNOS portfolio here, we've got 4, 5, 6, 7, 8, 9 days of training, and you'd need at least that. And if you want to cut down on the amount of formal training that you have, then there's going to be a trade-off because you'll need a lot more time to be spent on the job. And we've heard customers and users of SystemVerilog and UVM echo this story again and again and again and again. So it's a great methodology. It works well. The tools work well. The language works well. The methodology works well. There's been a massive increase in adoption of SystemVerilog and UVM over recent years, but don't underestimate the learning curve. At Doulos, we help with that by introducing a set of coding idioms called Easier UVM that we use on our training classes just to make it easier for people to get into UVM. So if you want further details on UVM in particular, well, you can download UVM from the Accelera website. There's a set of free resources, including videos, white papers, and source code examples on UVM on the Doulos website. So if you want to see some working source code examples, I'd encourage you to check out the video gallery on www.doulos.com. Have a look at the first steps with UVM video, and there you can find some references to complete source code examples that you can download. If you want to know any more about SystemVerilog, UVM, or training in any of the subjects mentioned on this slide, then do visit our website at www.doulos.com, talk to the Doulos reps at Verification Futures, or talk to us at Doulos, or talk to our partners, Test and Verification Solutions in India.
Have you heard your round of applause? We're going to go to questions in the audience to see if there are any questions from people. Yeah? Any questions at all for John? No? Okay, so thank you, John. Thank you very much for your presentation. There's no questions, so we'll let you go. And we'll move on to our next speaker. Thank you.